Section 4.2 Internal energy and enthalpy changes associated with chemical reaction. When a reaction releases heat, it's called exothermic. Q is negative. When a reaction absorbs heat, it's endothermic. Q is positive. Remember, the heat of reaction can be delta H or delta U, depending on the condition. Now let's define standard temperature. It's 0 degrees Celsius. However, in physical chemistry, many thermodynamic properties are given at the room temperature. The standard pressure is 1 bar, so it's denoted by P naught. The superscript naught in delta H naught also denotes the standard state. This superscript naught in the change of enthalpy of a reaction, with, again, this naught in the superscript denotes that every chemical involved in the reaction is in a standard state. And usually this is a hypothetical situation because it's impossible or nearly impossible to have all chemicals in the reaction in a standard state. You can look at more information in this website regarding standard state. The standard state is chosen by convention. 3 standard states are recognized. 1. For gas phase, it's the state of the pure substance in the gaseous phase at the standard pressure. P equals 1 bar, assuming ideal behavior. What about a gas mixture? That means the partial pressure of the chemical has a 1 bar partial pressure. For a pure phase, a mixture or solvent in the liquid or solid phase, it is the state of the pure substance in the liquid or solid phase at the standard pressure. Again, P equals P naught, very important. The solvent, the pure phase, is feeling this 1 bar pressure. For solute in the solution, usually it means the solute has a 1 molar concentration or 1 molar concentration under the standard pressure. Again, this solute and, of course, the solution feels 1 bar pressure. Furthermore, the solute is exhibiting infinitely dilute solution behavior. So now this delta U naught is simply delta U when all chemicals are in their standard state. Delta H naught is simply delta H when all involved chemicals are in their standard state. So now let's talk about the internal energy of the reaction. Usually we put R, uppercase R, in the subscript. That means we're talking about the change of the internal energy of the reaction system. And again, the heat of the reaction is delta U at constant temperature and volume condition. If we know the internal energy of the products and the reactants, we take the difference, that's the change of the internal energy of the reaction system. Similarly, the enthalpy of the reaction is delta H of R. And the heat of reaction at constant temperature and pressure condition is delta H. The change of the enthalpy of the reaction system is simply the enthalpy of the products minus the enthalpy of the reactants. Unfortunately, there's no way to determine the absolute value of enthalpy or internal energy of a chemical. So there's no way to know exactly what's the value of each product or reactant. However, it's possible to set a 0 reference, and then we can somehow define the enthalpy and internal energy of a chemical relative to the 0 references. So we have actually 118 zero references as of today. Why? there are 118 elements. So the 118 zero references are simply 118 pure elements in their most stable state of aggregation. Under the standard pressure, they have a zero enthalpy of formation at the room temperature. Again, this is the room temperature, not the standard temperature. The standard temperature is 0 degrees Celsius. However, when we define the zero reference for enthalpy, it's the room temperature being used here. The enthalpy of formation of any other substances, any compounds, can be determined through the enthalpy change of the reaction, starting from the reactants that are pure elements. For example, if we need to determine the enthalpy of formation of water, liquid water, we can look at this reaction. Hydrogen and oxygen are pure elements. And we do the reaction at 298.15 Kelvin temperature. That's the room temperature. And this 1 bar actually means, again, a hypothetical state. It means the partial pressure of hydrogen is 1 bar, the partial pressure of oxygen is 1 bar. At the same time, the liquid is filling 1 bar pressure. So it cannot be achieved. But somehow we can just use 1 bar hydrogen, 1 bar oxygen. And then, of course, in that case, the liquid water is filling 2 bars of pressure. And then we can do corrections. We can correct the pressure felt by this liquid water from 2 bars to 1 bar. We can calculate that part. So again, the enthalpy of reaction in the standard state is simply the products minus the reactants. And in this reaction, O2 and hydrogen 2, they are pure elements. Assuming both of them are in the standard state, then this is 0, this is 0. Therefore, the enthalpy of the reaction is equal to the enthalpy of formation of the liquid water. So that makes the calculation really simple. But again, it's really, really difficult to have all chemicals in the chemical reaction to be in the standard state. The reason we do this is because it's easier to measure the heat flow. If somehow we can measure the heat flow of the reaction under the standard condition, the value of this Q of R is exactly the same as the enthalpy of reaction, and it happens to be just the enthalpy of formation of liquid water. And that's how we determine the enthalpy of formation of the compounds. We have to use zero references. And the zero references are the pure elements in the most stable state of aggregation. Either it's gas, liquid, or solid at the room temperature under the 1 bar standard state condition. In general, if we have this kind of reaction, the enthalpy of reaction again is the products over here minus the reactants. Make sure you notice the use of the coefficients here. Nu x, nu y, nu a, nu b are the coefficients in front of the reactants and the products. Now, the absolute molar enthalpy is just defined to be the same as the enthalpy of formation. So again, this is just by convention. When you see molar enthalpy, it's not really the absolute value of the molar enthalpy of the chemical. It's actually the enthalpy of formation of the chemical, that is, relative to pure elements. If we look at ions, it's a little bit more difficult to determine the enthalpy of formation for those ions, because ions have to have different number of electrons than elements. However, we can just set another zero reference. We say the enthalpy of reaction for this one is 0. So that means we arbitrarily define the enthalpy of formation of H plus in an aqueous solution plus the enthalpy of an electron. Who knows what it is? But again, we're just defining this to be exactly 0. This is because the enthalpy of formation of hydrogen 2 gas is 0. And then we define the enthalpy of reaction is 0. Therefore, the enthalpy of formation of the product is 0. That means the enthalpy of formation of H plus is 0. Well, assuming the enthalpy of formation of this electron. Actually, this is not even a free electron. This is an electron in water. So again, this is just arbitrarily chosen zero reference for ions. When we have a zero reference, we can calculate the enthalpy of formation for other ions in water. How do we do that? Well, let's look at this reaction. Okay, so when we look at this reaction, we have this chlorine element on the left-hand side, chlorine minus ion in water on the right-hand side. So because enthalpy as state function, we can simply measure the enthalpy of reaction. For this reaction, we can have H2 and CO2 as the reactants. And then the product is H plus and chlorine minus in the aqueous solution. So this reaction, again, is the sum of these two reactions. We know this one is set to 0, this one is unknown, and then we simply need to determine the enthalpy of reaction for this one, and then we take the difference. We will get the enthalpy of reaction for this reaction that involves chlorine minus.